Welcome to Chapter 8, Day 7, talking about variation functions, Section 7.11. So today we're going to learn about two types of variation functions. One is direct and one is inverse. We're going to be very careful when we see these terms as well as what they represent. And once you get the hang of it, it's pretty simple, but the beginning does involve a little bit of thinking. So let's jump in. The first one we have is direct variation. Direct variation means a constant is multiplied by a variable. In other words, y increases as x increases, right? If they're both being multiplied, one side is multiplied, the other, they both increase. K is what's called the constant variation, or a proportionality constant. It's really any number, and we'll kind of see some examples. So for example, if we say y varies directly with x, we know that y equals a constant times x. Hence exactly right here. Y equals a constant, that k value, times x. You can also see that y varies directly with the nth power of x. Anytime you see directly, you're going to think of multiplied. So we have in this case y equals, you're being multiplied, so k times x to the power of n, or the nth power of n. Again, anywhere you see direct, you should think multiplied. On the other hand, we have inverse, which, as you can probably guess, is a constant divided by a variable. That means when y decreases, x is actually increasing. It makes sense when you have a solid number, then you divide, it's going to get smaller. So for example, if you have y varies inversely makes you think of divided. Y varies inversely, which means take your constant and divide it by x. You could have y varies inversely, so division, with the nth power of x. So this could be for any power. Y equals the constant divided by x to the power of n. And this n could be any number, and we'll see some examples below. But big thing, direct variation is multiplied, inverse variation is divided. So write an equation that represents the following descriptions. Y varies inversely with the square of x. Okay, I see the word inversely, so I know there's going to be division. So y is going to equal my k, or my constant variation, divided by the square of x, or x squared. Inversely told me to do division on the right side. The next one, x varies directly with the cube root of x. Directly is telling me multiplication. So y equals my constant times the cube root of x. So cube root of x. Very important that we find those vocab. I'm now going to jump to number 1 and number 4 on the extra worksheet. This extra worksheet you can find as Day 7 Notes Extra, possibly in your notes folder, or it's going to be called the Day 7 Practice in your practice folder. So take a minute, go to Schoology and find that. I actually have it on the bottom here. It looks like this. This is your Day 7 extra worksheet that we want to look at. In particular, we're going to look at number 1 and number 4. So number 1 says the number of workers W working for H hours to repair 30 automobiles. We are trying to figure out if that relationship is direct, inverse, or neither. Well, the only way we can figure it out is actually to write the equation and then see what kind of operation is happening between. So we know the number of workers W is going to be multiplied by the amount of hours they work. So let's say there's 2 workers, they work 2 hours, 2 times 2. And that's going to try to repair 30 automobiles. 30 is that constant, right? It's a number. Well, everything we've solved before, it's y varies directly or y varies inversely. That means there can only be one variable on one side. So in this case, it doesn't matter which one we're solving for because it's not being specific. But if I just got maybe w by itself, you'll see that it's going to be 30 divided by h. Hence, the division tells me that it's going to be an inverse variation due to that division. It doesn't matter which variable you solve for in this problem as long as you have one variable in terms of a constant with some kind of operation. So we'll do that with 1 to 3. Then 4 to 8 involves actually solving. So the first thing you have to do is set up the equation, and then we'll plug in some values. So for this one, it says P varies directly. Okay, P varies directly, so that means P equals my constant times Q. Directly is telling me multiplication. So this is my problem. If P is 12, so I'm going to plug in 12, and Q is 18, what is P when Q is 24? Well, the only way I'll be able to solve this is to first solve for that constant, which as you can see, it's going to be a pretty easy division. Solve for that constant, and then we'll plug in for when Q is 24. So when I divide both sides by 18, sorry, there's not a lot of room here, but we get right over here, K is going to equal 2/3. That's not my answer, but it's going to help me to find P when Q is 24. So back to my original problem now. This time I know P equals 2/3 times Q based on that K value. I'm going to plug in Q is 24 and I'm going to solve for P. 2/3 times 24 tells me P is going to be 16. So it wanted me to find P equals 16. Again, you set up your equation because it says directly, you're going to use multiplication. You'll have to solve for your unknown, and then it's a substitution with the value it's given. Okay, that should be a great start with identifying inverse and direct. And now we're going to go back to what's called our multiply property. So I'm going to head back to my notes now. Sorry if this gives you a headache. Okay, so heading back to our notes, we now have a multiply property of variation functions. You are probably aware we have a add multiply property, but now we're going to look at it in the lens of a variation. So we have to find multiply by multiply. That means the x's have to be multiplied and the y's from one point to the next. So multiply x by a constant and multiply y by a constant. We're going to identify the function represented. Then we're going to write its specific equation. There's a good amount of parts in here. So the first thing I kind of want to mention is when you are doing these problems, it has to be the same constant. I'll kind of explain what that means. So if I go from here to here, obviously, hopefully, you see it's times 3. Here to here, still times 3. So we're golden that we're going to be multiplying our x's by 3. Now our y's, from 5 to 45, you're going to be multiplying by 9. Keep the pattern going. You see that it's going to be consistent. Hence my multiply. Notice the left side is by 3, the right side is by 9. That can't happen. Like, we need the same base in a way. So another way to look at the right side is I can go from one to the other by multiplying by 3 squared. 3 squared. 3 squared, so that I now have a 3, and a 3. That's going to be extremely helpful because if you notice, they're both being multiplied by a power of 3. The x's is by 3 to the first power. The y's are by 3 to the second power. So because they're both multiplication, this is going to be our direct variation. Because they're both being multiplied. How do we get that? Okay, it's going to be y is very directly, so k times some power of x. Well, we know that power now. We just found it as being 2. So x squared. So this is a direct variation. Y varies directly with x squared. That is the general equation. However, we want specific. So just like all of our models, we have the general base, and now we're going to plug in a point and get the exact specific equation. So it never matters what point you plug in. I like to choose the easiest, so I think actually 1, 5 is going to be the nice point. So I'm going to plug in my point 1, 5. So that means I have the 1 for my x, and my y is 5. Just like we did in the example pages, we're going to solve for k. Solve for that constant, and this one's pretty easy. K is going to equal 5. That's good and dandy, but I need to actually apply it to my problem. So this problem, my specific equation is going to be y equals 5x squared. And that would be the graph of the direct variation. Let's try another one. Same idea, we're going to look on the left side. This increases by 3. By 3. Now the right side. You can see already that it is decreasing. So it's decreasing. So I'm actually going to go all the way up to my notes already. Oops. Right to this idea. Y decreases as x increases. That's hinting to me that I'm probably going to have inverse. Let's now confirm it. How do I get from 162 to 18? I'm actually going to divide by 9. Divide by 9. But you're like, this is the multiply property. Well, yeah, it is. It's the same thing as multiplying by 1 over 9. Gotta excuse the bells. Since it's multiply, I notice it's going to be times 1/9 from each y value. And thinking about what we mentioned before, we want to get that same base. Now, in this case, we're going to be a little flexible. This is 3. To get 1/9, we either can look at it as timesing 1 over 3 squared, or you can look at it as dividing by 3 squared. So many ways to look at it. I'm putting all these options. You take the one that makes the most sense to you. But in the end, you have to realize you are multiplying by a power of x squared. The power of x is 1/3. So because you are dividing, or you're multiplying by a fraction, it's going to be our inverse. And I know that's very confusing, so we'll do more examples, but this is going to be an inverse variation. Y is inversely related with our x squared, our x being the 3. It's by 1/3 raised to the second. Now that is the specific, so we now need to plug in a point. Pick a nice point. I might pick 1, 162. Y is 162, X is 1. Solving for our constant there. Pretty easy again. Constant equals 162, which leaves us then with our inverse equation, y equals 162 over the square of x. We knew it was inverse because the y values are decreasing and because you are multiplying by that fraction or dividing as you go. Okay, let's turn the page and go through one model example, and then you'll be free to go. So the intensity of light reaching you from a light bulb depends on how far from the bulb you are standing. That makes sense. Suppose that at 3 meters, the intensity is 120 units, and at 6 meters, it is 30 units. Okay, back to models. First thing we always do is write our variables. So it looks like we have D can be our distance. I'm going to specify in meters. And I'm just going to use I for intensity of that light bulb. And that's going to be just by units. It's called 120 units, 30 units. I'm going to make a nice table, just like we had above. I'm going to create it though. So I'm going to have my X and my Y, depending on how you labeled it. I know at 3 meters, I have 120 units of intensity. And at 6 meters, I have 30 units of intensity. Already noticing my Y's are decreasing. Hint, 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 we're going to have inverse. So I notice from my first point to my second, I'm going to multiply by 2. From my first point to get to 30, so 120 to 30, you're going to be multiplying, because it's multiply, over 1 over 4, or divide by 4, which really is 1 over 2 squared. The reason why I fought for that, or worked really hard, is to get the common base. I know the base on the right is 1/2, so it's not truly the same base, but it's getting that constant the same. So from all of this, I am able to identify that this is going to be inverse. Okay, we're dividing. Write the general equation. The general is just y varies inversely by x squared. This 2 right here is telling me that it's squared. So it's an inverse variation. I can write variation. And then it just wants the general, so this is as far as you need to go. Part B, predict the intensity at 12 meters. Well, notice that could be an extenuation from our table. So if I just keep going down, 12, I'm trying to predict the intensity. From here to here is still times 2. From here to this unknown is going to be the same times 1 over 4 or times 1 over 2 squared. However you want to do that, you'll land with 7.5. So the intensity is 7.5 units, and that you can get just from predicting from your table, kind of extend your table. Now part C, let's get into the nitty-gritty. We want the particular equation. So that means just like above, we're going to plug in a point, we're going to solve for our constant, and then we will have our exact particular equation. So from above, we knew the equation is y equals k over x squared. one of our points and you have the power to pick whatever you want. Just because 120 is pretty big, I'm going to choose this point. So I'm going to plug in 6, 30, but the choice is yours. 30, the denominator is going to be 6 now. So we do have some algebra we're going to be plugging in. So solving for k, we're going to get 30 equals k over 36. So k is going to equal the product of 30 and 36. So little k here is actually 1,080. That's my constant. So I took my general equation, plugged in a point to find the constant to give me now the particular, which means it's 1,080 over x squared, because we're inversely related with the square of x. Now, since you have that equation, the rest of the time we can just use that equation. Predict the intensity at 10 meters. So again, meters is my x variable. Yes, I did use d and I. So if you want to go back and call this x and y, we can. Sometimes at the beginning it's easier to look at it with actual letters, but it is your call throughout as long as you explain it to us. X is the distance, so we're going to go ahead and plug in 10 meters for my x. I'm going to show exactly what that looks like. That 10 just goes right there because it is my x variable. So when you solve, you'll get about 10.8 units. Make sure you're putting units because that is our intensity. Predict the distance at which the intensity will be 4. Again, using our particular equation this time, 4 is going to be the y value. That's the intensity. We're going to solve now for my x. Cross multiply, you'll get 4x squared equals 1,080. Divide both sides by 4, you'll get a 270, square root. I'm getting x to be approximately 16.43 meters. And that would be the distance at which the intensity would be 4 units. Part F is going to be our graph, which, as you can tell from all of these problems above, we have just made a bunch of new points. So let's take a quick moment and just put all our points down here. From the table, we already know 3, 120. From the table, we also know 6, 30. We found 12, 7.5. From part D, we found 10, 10.8. And from part E, we just found 16.43, 4. So we want to get all these points nicely on our graph. We need our scales. So let's make sure we get our scales and labels. So this is going to be distance. That's my x variable. It's in meters. My y is my intensity. And that is just in units. We want a proper scale, so it looks like our x's are from 3 to 16. We know it will keep going on, but at least we need to get those. So we can actually go by every one. 1, 2, 3, 4, 5. This would be 6. What other one do we need? 7, 8, 9. This would be 10. We need 12 and 16, so that definitely fits our values. And for our y's, we have to go all the way up to 120. Wow, okay. So maybe I scale by tens. 10, 20, we need 30, 40, 50, 60, 70, 80, 90, 100, 120. Yeah, that seems like a good amount. And now plot your points, so take a moment. 3, 120, 6, 30, 12, 7.5, 10, 10.8, and 16 is like 4. Hopefully you see that little J curve. You're going to go ahead and graph it, connect, and then we have to be smart about it. Yes, you can put your arrows in a way because you know it's going to get really, really high. Once you are 0 away, it'll probably stick at an amount. So if you wanted to actually find that 0 and put a point, not going to be incorrect. But we also have to realize the intensity, it could get to 0. But thinking about our lens about exponential, we're going to keep that nice horizontal line. Okay. We'll talk about a lot of examples as always, but this should be the general idea with your graph. We knew it was inverse, and then we were able to find our points. If you have any questions, please bring them to class. This is just day 7, so we have plenty more days happening. And good luck.